Okay, so I wrote something on the board for you to think about. Okay, what's the first thing that you did? Did anybody, think about what they look like? Okay, so you graph them, okay? X cubed plus 4 is the first one that I wrote down, right? What does that look like? X cubed plus 4, right? And then y equals x squared. Looks like that. Okay, so you thought about the graphs. Okay, great, and then what did you guys do?
Nothing.
You did nothing.
Sure.
Okay. Did you talk about what you would do?
We were talking, but we didn't.
Okay. If I'm talking about area, what do you think it's going to involve? It's probably going to involve integrals of some sort, right? Okay. Julia, did you do anything with integrals at your table?
We had to use them, but didn't really know.
Okay. What should we use with them? Okay. Now, if we were to do an integral, what might the limits of integration be? Okay, I gave you 0 to 1, right? Okay, so if you do the integral of x squared from 0 to 1, that's going to find you this area right here, right? Okay. If you do the integral from 0 to 1 of x cubed plus 4, that's going to find you this area right here. So what are we going to need to do with our areas? Okay, if we subtract out this guy right here, you have the area in between, right? Okay. That's all we need. Okay. When we talk about the area in between two curves, okay, when we talk about just the area under one curve, our integral, you don't have to write this down, this is what we talked about last chapter, this is what we worked on for weeks and weeks and weeks, right? Our integral is adding up all of these itty bitty rectangles that represent area, okay? Well now, if we have the area between curves, then we need to subtract out that lower area, okay? So whatever function is above, that needs to come first. The integral from a to b of our top function minus, we have to subtract out that lower function and what area is in between that and the x-axis, okay? Or instead of two different integrals, what have we talked about? If they have the same limits of integration, can we just put it all together? Right? So what you need to know is that if we're talking about the area in between we're going to have the integral of f of x minus g of x dx, where g of x is above, or f of x is above. It would be our top function. G of x would be below our bottom function. So a couple things are going to be important here. We need to have a picture, okay? And when I presented you with that problem on the board, some of you thought about the picture, some of you didn't, okay? But you need to have a picture so you know which area is going to be more, okay? Which function is on top and which function is on bottom, so you know whose height is the one that you need to be subtracting out, okay? So we need a picture for that. in what I put on the board, I said from 0 to 1. That's not always going to be the case. So sometimes we're going to have to find the intersection of our two graphs, or maybe we have 3 graphs all squished together. Okay? But we might need to find some intersection points so that we know what we're working with. Okay? So a big part of this is going to be drawing an accurate picture so we can set up our integral. Okay? And that's probably where more of your work is going to come. Okay? We know how to integrate. And so that's really not what I'm as concerned with right this second. Okay? I'm concerned today about drawing our picture and getting our integral set up properly. Okay? So we're going to go through 3 examples we're going to do without our calculator as far as the setup is concerned. And then I have one calculator type problem that we'll do. Okay? So I want to find the area of the region bounded by these 4 equations. Okay? So sometimes you'll see that word, the area of the region bounded by. You'll see that bounded word, and then it'll give you equations. Or it'll say find the area in between these 2 curves. You'll see it written a couple different ways. So what I want you to do right now, take those 4 equations and put them on a graph on your notebook. Take those 4 equations and put them on a graph.
Confused.
Are you leaving us?
Yeah.
Okay.
I'll watch the video.
Perfect. Okay, so here are your 4 graphs, right? So what's the region bounded by these 4? Where does that exist? Okay, so I'm going to use my highlighter here. Right here?
Yeah.
Okay, so I would really lightly with your pencil shade that in so you know which region it is. Okay. Now this one, it's actually pretty easy to know what your limits of integration are because they kind of give it to you, right? They don't give you the interval, but they kind of do by saying x equals 0 and x equals 2, right? So we know we're going from 0 to 2. Okay. Now I know that you don't know any different, but tomorrow we are going to work with doing this in terms of y's instead of x's. So I want you to think about how we have these little rectangles sitting in here that we are finding the area of. Okay. And I'm going to actually ask you to draw this really skinny rectangle in your region. Okay, for a couple different reasons. Tomorrow we're going to work with y's, and so by drawing this rectangle, we know that the thickness is dx because it would sit along the x-axis if you stretched it all the way down. But we also can see the top of the rectangle and the bottom of the rectangle. The top of the rectangle is sitting up here on this line, x plus 6. So it's our top function. The bottom of the rectangle is sitting here on x squared. So we know we need x plus 6 minus x squared to get that full height of the rectangle. And then we have an integral. Okay. Now in your homework, I do have 2 problems I make you do without a calculator so that you keep your integration skills in tip-top shape. But the other 1, 2, 3, 4 problems, I'll let you use Math 9 on. Okay? So to save us some time right here, if you Math 9 this, what do you get? 34. I would prefer the answer of 34. So please make sure you can get this in Math 9. Did that glue stick up here also? So I found this in the hallway. And then this glue. Keep them. Oh, well. It was a good one. What happened? Okay. Are we ready for the next example? Are there questions on this one? Okay. So write this down. And then draw those 2 graphs. Write those down and then draw those 2 graphs. Did I ask you whose parents are coming tonight? Anybody else's? Here's them. Sorry that I'm a good child. Okay, this one looks kind of strange, right? We have the parabola and the line. It's almost like half of a teardrop. A banana. A banana drawn by a small child. Right? Good. So this is our region. Okay. So here's our region, and we have these rectangles that we're going to add up the area to with thickness dx. So we have our integral. Our limits of integration are not obvious this time. Boy, we know where it begins, right? Where does it begin? 0. Dylan, where does it end? Okay, this intersection point. What is the intersection point? That's the coordinate 2, 4. How'd you come up with that, Max?
When like x is 2, you know, like 2 squared is 4 and 2 times 2.
So you wanted x squared to equal 2x. Okay, if we didn't have our calculator, you would need to be able to find this. Okay. So if x squared equals 2x, I think Max just played around with numbers in his head, which is fine. I have no problem with that. But if you need the algebraic way to get that, we would have to set equal to 0 and factor. There are our 2 intersection points. Okay, that one we can probably see without algebra, but if you couldn't see it with algebra, that would be what we would need to do. Okay, so which function is on the top?
2x.
Okay, minus x squared is our function down below. Let's do this one by hand, because we can. And I will expect you to on, I think our quiz next week will be some problems without a calculator, some problems with a calculator.
I did. Yes.
You're welcome. What? That would have been rough news. Okay, antiderivative for 2x. Minus 1/3 x cubed. Someone's already gotten there. Love it. So we have 2 squared minus 1/3 times 2 cubed minus 0. It doesn't really feel like we've learned something new today. No. It does feel like that? How to graph. Okay. Okay. Just curious. True. Is it that much more intense than just setting an integral? Really not. Now, this next example might be where like we see a really big difference. Okay. What I want you to do here is I want you to graph this. Ooh, x equals y squared. What does that look like? Well, but both of them. We would need the full sideways parabola. Because it would be radical x and negative radical x. Brem is not impressed. So write it down, drop it. Okay, does your region look like this? Okay. Now, when I pointed out that x equals y squared, Huntington asked, well, about y equals radical x. Yes, and y equals negative radical x. So if we were to solve this for y, we would have y equals plus or minus radical x. So when we're thinking about our equations in terms of x, because we're going to integrate with respect to x, we have this red equation that I highlighted is y equals radical x. This green equation is y equals negative radical x. Go ahead and label these on your graph also. And then this blue line is y equals x minus 2. I know in our other examples we really could tell which graph was which, but we might get some regions that have 2, 3, 4 graphs that maybe 2 of them are quadratic and 2 of them are linear. You might want to label which graph is which so that you don't get mixed up with top function minus bottom function or which intersection points you need. Okay? Okay, so what's our top function for this region? Radical x. What about our bottom function? It's not a could. You have to split this up into 2 different regions because our function on the bottom switches. So the rectangles over here are different than the rectangles over here. Okay? Where does that switch occur? Okay, so what's the x value of that intersection? Maybe we should figure out our intersections before we go any further. When do these two equal? Okay. So when does y squared equal y plus 2? Right? If I'm going to set the x's equal to each other, right? Okay, so when y is negative 1, what is x? Okay. And when y is 2, what is x? 4. So our intersection points, the ones that we care about, are x equals 1 and x equals 4. Okay. So if we split this up, for Pierce's suggestion, from 0 to 1, these rectangles, their top sits on radical x minus the bottom of the rectangle sits on negative radical x. Okay. And then we would add to it the area between our 2 curves from 1 to 4. And these rectangles, notice how the top is still on the red function radical x, but now we have to subtract out the blue function x minus 2. Now this is one that we could integrate by hand. But I will let you math 9 this to get the answer. Does it give you a rational number, or is it pretty ugly? Does it change the fraction?
Those are the 2 numbers.
What do you have to do? 4.5? 4.5, what comes after 5? Oh, 0, 0?
Well, for the one part.
For the one part?
There's 2 parts.
They're both together?
Yeah. Oh, really?
Well, but you said so you did get 4.5.
Oh, I did. And then I added it again. Okay. This is
So your calculator is pretty sensitive. If you're subtracting, so like this is a different button than this, right? This is subtraction, and this is the negative sign, okay? And if you type it in, sometimes it'll say like syntax error, but like in this case, if you make both of those the negative sign, it just assumes you're multiplying, and so what it did for your calculator, like it multiplied them together, okay? That's like their third or fourth time that's happened to people in the past 2 days. That's why I wanted to talk about it. So just be careful which sign you're using. Yes. In terms of like breaking it apart into two, not necessarily, but like these antiderivatives, I don't think are too difficult to do without a calculator. But like on the quiz next week, I would say, like, I probably want to make you split it into two. Okay. All right. So the last example I want to do, this is an AP question, multiple choice question, just taken off of a practice test. So you can use your calculator. They give you the graph. How thoughtful of them. But what you need to do is you need to figure out how to set up your integral to find the area of that blue region. So I will give you 2 minutes, maybe 2.5 minutes, to work on coming up with how to set it up and punching it into your calculator. Feel free to work with your pod mates. I know that they gave you the graph, but are you going to still have to graph it? Yes, you will. Because you need something very special about that graph in order to be able to set it up. Those of you with a color calculator, very helpful. Know which one's on top. Yeah. Mm-hmm. Oh, you still have to guess. You have to enter one more time. There you go.
Yeah. Yeah. Please tell me, can I change my calculator?
Mm-hmm. Oh, actually, that's a good idea.
I want to tell you a story that happened last night. It's not that.
Okay, so do we have it?
Yeah.
Wow! I had 2 boxes that I got, I think, a week ago. Thank you for letting me know. Because you know what? You're the first person all year to actually do that. Sometimes I look over there and they're just like gone. I don't know. I will go to the office. Okay. Your integral is from 0 to what?
1.139.
Don't assume that that's 1. You actually have to find the intersection. Okay? And then which function is this right here? So this is what you needed to type into your calculator. Now, how many of you graphed those 2 to find the intersection? Okay, so when you actually do Math 9, and I did it on this calculator, I probably should have done it up there, but it's going to take too much time to get it up. So when I hit Math 9, and I put 0 to 1.139, I'm not going to type in e to the negative x squared. I am going to bring up if I hit alpha F4, I can select Y1 minus alpha F4. I can select Y2 dx. If you have not everybody does that. If yours doesn't do it, then you can go into bars, right? Bars, and then go to Y bars function, and then you can select from there. But I could just say Y1 minus Y2 because I've already typed them in, and boom, B is my answer. Okay. So if you have a calculator like mine, alpha F4 are the shortcuts to get to Y1, Y2. Otherwise, if you hit the bars button and arrow over to Y bars and function, then you can get there that way. Okay? But that just saves you from having to type it in all over again. All right, so on your homework, everyone look at the gold sheet. Do you see where it says no calculator next to a few of the problems? From beginning to end, there will be no calculator. Okay? The other ones, I want you to set up, and then you can use Math 9. But try, if it says nothing about using a calculator in the instructions in the book, I would be expecting you to graph those without your calculator and find the intersections without your calculator. It's more just the Math 9 I want you to save some time with. Now, is anybody wondering why this was a positive number? I'm going to go back to that last example. Did anybody expect that to come out to be negative? If I asked you for this area, what kind of area would it be? It would be negative. But I'm taking this area and I'm subtracting this area. What happens when you subtract negative? Turns to positive. Okay? The area in between curves is always, always, always going to be positive. The area in between 2 curves will always be positive because of that right there. We're subtracting the negative, and so they add together. So how could this be helpful? All right, if you could model something with functions, you might be able to find the exact area as opposed to using like geometric shapes to find it. Okay, engineering peeps, this is something that's helpful. Okay. All right, we have about 4 minutes left in class. If you need to get organized with your new gold sheet, taking a picture of the book problems, whatever you need to do.